원래 HDMI 2가 화장실에 가서 맞아. 연결 잘 됐는데
You click auto?
맞아. 근데 난 월코 안 했어. 괜찮죠? 아니 뭘도 안 했어.
Only within the other room the cable worked, so it should work. Okay, so let me start. They will fix it. Hi everyone. So I hope this was okay for everyone. Hopefully, maybe time was a bit tight. I don't know, but everyone has the same problem, so you don't need to worry about it too much. So last time we introduced. Okay, so now I think let's start. Okay, so we introduced two important formulas. We learned that. Okay, you guys can talk more after the class, okay? So we learned that particle numbers are usually very large. So we don't want to deal with these large numbers. That's why we learned that we can introduce the so-called Avogadro constant. 6.022 10 to the power of 53 inverse mole.
아니 아직 얘는
And
나가는데
we can divide by this one, and then we get mole units. So this is the mole number. It tells us how many moles of particles we have, because we don't want to always deal with these large numbers. And you remember this Avogadro constant looks weird, but it was defined so that the carbon atom, the carbon 12 atom, is exactly 12 gram per mole, right? So carbon is 12 gram per mole, carbon 12. And then, based on this, we also learned that we can also take the mass of the whole substance and we divide by the molar mass, that is how much gram one mole is weighing. And then we get exactly again the mole number, right? So these two relations are important for us. Here also be careful, because SI unit of mass is usually kilogram, while molar mass is usually written as gram per mole, so you need to always convert usually the unit, right? But otherwise, this is pretty straightforward. It means that if we have the mass and we know what atoms it's composed of, we can always know how much mole and how many particles are in there, right? The assumption is always that we have an ideal substance which is like exactly composed of these atoms, right? Or these molecules.
조작이 됐는데
Yeah, since the cable is not really working.
HTML 1로 바꿨죠.
The auto scan doesn't work, right? Did you change the HTML?
I'm not sure, but like that machine is just really slow somehow.
It's supposed to, when you hit auto, it was
Yeah.
But it doesn't change, it's like continuously HTML2. Okay, I just continue like this. Okay, so this was the molar mass of substance, right? And if we have like a compound, we just add the molar masses of all the compounds together, right? So let's say we have a molecule like CO2, and we want to get the molar mass. We just take the molar mass of carbon plus 2 times the molar mass of oxygen, right? And here, as I told you last time, this would be usually the average over the isotopes, right? So you would usually need to take that one from the periodic table, which is already the average over all the isotopes that occur naturally. And then you can just take that number there, insert it here, and you get the molar mass of a molecule, right? Now, ionic substances are a bit different. Ionic substances, like consisting, for example, of sodium chloride, they don't have like a molecular unit, but you can get the molar mass of one of these entities that build up the crystal. So in sodium chloride, for example, you have this regular arrangement of the atoms. So chloride here and sodium. And they will arrange periodically in the solid crystal. But you can see the unit that is always repeating here is the sodium chloride. We usually call this the unit cell. So there's some kind of repeating unit that occurs. So, sorry. So sodium chloride would tells us the stoichiometry of the crystal. Okay. Okay, so we have exactly 1 sodium and 1 chloride in that ratio. So we can calculate the molar mass of this one, but this would exactly equal the molar mass of the whole crystal, right? Because it's a molar mass is also an intensive property. It's important to know, right? You remember we had intensive and extensive properties. What other intensive property did we have? Density, right? And extensive, we have so far n, small n, mass, right? All of these are changing with the system size, right? Okay. Can you maybe go a bit to the side? Okay. Sorry for that. I will just continue like this. But there's a problem with the beamer, I think.
Yes.
So maybe you can get Changjiu.
Just left for his lunch.
He went for his lunch, of course. Yes. Okay, we have a lecture on the board today, it seems. That's fine. Okay, so. Okay, it will be a bit complicated to do this, but let me see. Yeah, both of them have a problem.
Maybe later on, we might call this one.
Okay, so example here is calcium carbonate. I need to actually turn this so that I can see it. Calcium carbonate. It's also called calcite. You find it in limestone. And the task is to calculate the molar mass. So this is also a solid crystal. It's a repeated unit. But as we know, it doesn't matter. We just need to know the repeated unit, right? Because molar mass is intensive property, so if we know the repeated unit molar mass, it will be the same as the whole crystal molar mass. Okay, so how do we do this? So we just take the, we can simply take the molar mass of calcium plus molar mass of carbon plus 3 times the molar mass of oxygen. So the stoichiometry tells us exactly how much we need to multiply them with. The calcium is 40.08 gram per mole. So the way is a bit different than on the slides, but I prefer this way, so I will just show you this. Plus 12.01 gram per mole plus 3 times the molar mass of oxygen, which is 16. Okay. And this would be 100.09. Okay, so this would be your molar mass. Okay, second task would be now to have a certain sample which is 4.86 moles. And the task is how much mass is it, right? And then also what is the mass of carbonate ions? Okay, so how do we calculate this? Okay, so we already know that 1 mole weighs 100.09 gram, right? If we want to get this one, we just use our equation. We know that N equals the mass over the molar mass, which means the mass would be N times M, right? How much is the mole we have here? We have 4.86 mole. Just multiply this with the molar mass, 100.09 gram per mole. And we have our mole number, which is, sorry, the task was to calculate the mass. So I made a mistake. The mass, it is then 60. 1 second. To get this on the right slide, what was the mass? 486 grams. Yeah, it should be around that, right? It's 4 times 100. So this is the mass of roughly 5 mole calcium carbonate. Okay? And now you should get the mass of the carbonate ions. So how do you get that one? Well, you can simply get the molar mass ratio of the carbonate. You can multiply that with this mass. So then you get 60, so you get 292 grams. So this would be one way to do it, right? Just get the ratio of the molar masses. And, wait 1 second, molar mass, this is N. Oh no, sorry, this is this 486 grams. So you just take the molar mass ratio, which will tell you how much of that mass is attributed to the carbonate, right? The other way would be you just go over the mole. So you say like 1 mole of carbonate, how much does it weigh? So you calculate for carbon atom what would be the molar mass is 12. So you multiply that. You just get 12 gram for 1 mole, and that's the way that they do it on the slides. But this way should be maybe a bit simpler. But yeah, feel free to also check out the other way to do it. I almost have no way to look at you, like, because I need to constantly concentrate and look here and here. Okay, so if you have a question, just say here or something like that, right? Or stop. Anyone wants to say stop? No, right? Okay. One more example. Isopentyl acetate. I think I need to make space again. That's why I'm getting hot. Isopentyl acetate, which is C7H14O2. Okay. This is a compound responsible for the scent of bananas, and interestingly, bees release about 1 microgram of this compound when they sting. The resulting scent attracts other bees to join the attack. How many molecules of this compound are released in a typical bee sting? Okay, so it's again packed in a story, but ultimately what you have is the mass, and what you want to know is how many molecules, right? And then how many atoms of carbon are present. Okay, so how many molecules is very easy. You just use the same equation as always, right? N equals M over M, right? So you need the molar mass of this compound. We get this as 7 times the molar mass of carbon plus 14 times molar mass of hydrogen plus 2 times molar mass of oxygen. Yeah. What is this? Actually, they have it in the slides here somewhere. It's 130.18 gram per mole. Now that you have the molar mass, you can insert this here. 1 microgram divided by 130.18 gram per mole. Need to make sure that the units are the same so that they cancel out. 1 microgram is 10 to the power minus 6 gram divided by 130.18 gram per mole. And you get the number of mole. I think they didn't calculate because they use a different way. No, they calculate. 8 times 10 to the power minus 9 mole. Now you know the number of moles. So getting particles, you use the second equation that we had. Remember, n equals capital N over Avogadro constant. So n would be small n times NA. So it's 10, 8 times 10 to the power minus 9 mole times 6022 to the power 23 per mole. And you get 5 times 10 to the power 50 molecules. So it's really easy. I mean, it's just using these two equations in all kind of variants, right? And then if you want to get the number of carbon atoms, you just multiply it by the stoichiometry, right? So this is the number of C7, H40, O2. You just multiply this by the number of carbon atoms per molecule, which is n carbon over n. Well, actually, let's divide this as n. So it's like 7 over 1. So this would be the number of C atoms per molecule, right? And then you get this is atoms per molecule. So then molecule cancels out, and you get 4 times 10 to the power of 16 atoms, carbon atoms, right? So it's two equations that you need to know, and you need to know that you can always make use of the chemical formula to calculate the number of atoms, right? Because the chemical formula tells you everything about what is the ratio of atoms to molecules. Yeah? Okay. Yeah, so they noted also that they were not super careful here with the significant digits. So in principle, you should just, as we always discuss, pull the significant digits until the very end. So I like always take the numbers that you get out of the calculator, and only in the very end round to the significant figures. Right? So that would be the usual way. But if they ask you to report preliminary results like this one, then just report it already with the significant figures. Right? In this case, they rounded to one significant figure because the mass was given as one significant figure only. Right? So that's why they reported this here. And then in principle, when you insert it here, you can first use the more exact number, and then later round it. Okay, so there are more exercises to calculate some molar masses, but you can do that at home. And to calculate number of nitrogen atoms. So you can find on the slide, you can use it to practice. And now the join-in, I guess you have all the slides in front of you. Everyone has slides in front of you, not everyone, right? Okay, so we have 4 molecules given, which is water, CO2, ammonia, and C2H6. Okay. The molar masses for the different elements are given here. So hydrogen is 1.008 gram per mole. O 60.0, N 14.01, carbon 12.01. And the question is, for which of the following compounds does 1 gram represent 2.27 times 10 to the power minus 2 mole? So the mass is 1 gram, and the mole is 2.27 times 10 to the power minus 2 mole. A, water, B, CO2, B, CO2, C, ammonia, D, ethane. What is the right answer here? Need to do a quick calculation, maybe. It's water, CO2, ammonia. Okay. You guys can do it. Need to put it in your calculator. At least it's up to 2. You know how to do it, right? Calculate the molar mass of the molecule and use our regular equation. Okay, any answer? Who is for A? B? Ah, that looks much better. Okay, everyone, I think, calculated it almost. Okay, next one, the mass of 0.82 mole of a diatomic molecule is 131 grams. Maybe we skip this one. It's the same equation and you guys already know how to do it. Okay, maybe this one. Which of the following 100 gram samples contains the greatest number of oxygen atoms? Okay, so the mass is 100 grams. Is it water? Is it B, H2O? Is it C, C3, H6, H2? Or is it B? All of them have the same number. You can feel free to talk to each other if you want to do it together. It's totally fine. We don't need independent statistics here. Can be dependent. So how would you do it? In this case, how do you calculate this one? Well, let me first ask to see how many already got the answer. So this is A, B, C, D. Okay, I think most of you already got the answer. So how do you do it? You calculate you get the number of moles, right, of for each molecule. So you N equals M over the molar mass, and you get the moles of the molecule. And then just multiply this by number of O atoms per molecule. Right? And that's it. Okay. Good. Okay, I'm just gonna skip over this problem solving thing for now because I think we can do this better with examples. So what I will talk about next is the so-called mass percent. The mass percent. So what is mass percent? The mass percent is the mass of an element in 1 mole of the compound divided by the mass of 1 mole of the compound. Right? Okay, so this will tell you something about how much mass is attributed to each element, right, of a given compound. So we do another example. Carbon, which is a substance that occurs in 2 forms, having different arrangements but the same molecular formula, which is C10H14O. And then one type of this carbon gives caraway seeds their characteristic smell. The other type is responsible for the smell of spearmint oil. Compute the mass percent of each element in carbon. Okay, so what is the task? The task is to calculate this one, right? What do we need to know? What information do we need to find the mass percent? We need the mass of each element, and we need the mass of the compound. Right? Okay. So how do we approach this? We calculate first the mass of carbon in 1 mole. Of the substance. So this would be 10 mole, because we have 10 carbon per molecule, and multiplied with 12.01 gram per mole, molar mass of carbon. And then we get 120.1 gram. Okay. So one trick is in these questions to always do everything via mole. Yeah? So if you always convert everything to 1 mole, then usually things will work out quite nicely. If you use the equation way, sometimes you have to think in another direction again. But if you just use the way over the mole, then things are quite simple. You can do that for hydrogen as well. Then you get for hydrogen 40.11 gram. You get for oxygen 16.00 gram. Now you have the mass of each of the atoms in 1 mole, right? And then you simply just take the sum of them to get the total mass for 1 mole. Well, this is just the molar mass. molar mass multiplied with 1 mole, so it's just the molar mass, right, which is 150.2 gram. Which is just the molar mass times n, where n is 1 mole. So now you choose 1 mole of this and 1 mole of this. You can directly compare this, right? And now you can just divide them with each other. So then for carbon, you would get 120.1 gram divided over 150.2 gram. And this would be 79.96%. Okay. So essentially what you did is you can also write this in a different way. You can write this as the molar mass of the element divided by the molar mass of the compound times the atom fraction. Right? So this is the way how I usually quickly calculate it, but it's also good to write this in one more to understand better. But essentially what you're calculating is just the ratio of the molar masses, right? And you multiply it with how many atoms, how many atoms of that element you have per molecule. Yeah. It would be the same thing. Okay, and we can do the same thing with hydrogen and oxygen. I will not write the numbers here, and they will add up to 100 if you did everything correctly, obviously. There are some more exercises to this again, so feel free to use one of the two ways. Either you use this way or you use this way. Both should lead you to the same result. Now there's another join in. Which of the following 100 gram samples contains the highest percentage oxygen by mass? By the way, usually for this mass percentage, we use a simple X. The book doesn't really like those. No, sorry, it's a B. Sorry, X is for mole fraction, B is for mass fraction. So, for example, BI would be an element would be MI over the molar mass of the compound times the number of compound. Right? Okay, so now the question is, which of the following 100 gram samples contains the highest percentage of oxygen by mass? Okay. So highest oxygen. Sorry. Is it A, water? Is it B, N2O? Is it C, C3H6O2? Or is it D, CO2? Or E, or Z? Okay. Let's give you a second again to calculate that. Okay, everyone got an answer? So who thinks it's A, water, B, N2O, C, D, or same? Okay, so how do you calculate it? Just use this formula. That's what I would do. Take the molar mass of oxygen divided by the molar mass of water, and then multiply by number of O per compound, right? So for water, it would simply be, what's the molar mass of oxygen? 16, right? 16.00 grams per mole, divided by molar mass of H2O, which is, let's say roughly 18.016. 18.016 grams per mole. And then how many oxygen per molecule? Just one. So it's 1/1. And you have it, which is around 80.8%. And if you do that for the others, you realize that you have a smaller fraction because N is heavier than H, right? So this will automatically become larger and then this becomes smaller. Right? So without calculating, you can immediately know that the fraction here should be smaller because just the total mass of the molecule, the molar mass, is higher. Here also you can directly see this because 3 carbon atoms, right, will be a large molar mass. 3 carbon atoms will be around 36. Now here you have to multiply this with 2, but still if you calculate this, this would be smaller than this number. Right? Okay, so you can use this way to calculate the mass fraction. Okay, so now you know about these chemical formulas. I wrote them all on the board. But one question you might ask is like, how do we actually come up with these formulas? Like, I mean, we always take that as a given to have this formula, but let's say we have a compound we don't know what it is. Like, how can we determine the formula, right? And usually the idea is to do a lot of weighting and chemical reactions. So you weigh the sample before, then you know the total weight, and then you start doing some kind of chemical reactions to decompose the molecule into its elements. So let's say you have a molecule consisting of hydrogen and carbon, let's say C2H6. You can then decompose this into CO2 and water by reacting it with oxygen. So then you can measure the mass of these products, and if you can write down the chemical equation for this, then you can actually back calculate the exact ratio of carbon and hydrogen in the original compound. So this is usually called elemental analysis. This is the traditional way people have done this. These days, nobody's doing this anymore, just using mass spectroscopy. But that was the traditional way to do it. So usually we call this a combustion device because we are essentially burning that compound and decomposing it into the elements. And as a result of the analysis, you are then basically given this mass here, this mass, and this mass, right? So these 3 are given, and you have to determine x and y because they are given. And you should determine x and y. That's usually the task that you have to do. Okay, now I cannot show you how the device looks like. Some of you can see it on the slides. We are on slide 72, by the way, for those who could follow. So we have the sample in some kind of... now I need to draw something. I'm really bad at drawing. Okay, so we have here our sample. And then we put this into some kind of furnace, yeah, to burn it. It will evaporate into its reaction gases, which are CO2 and water. And the water will be absorbed using magnesium perchlorate. So here, this is filled with a solid, which is magnesium perchlorate. And apparently, this one is really good water absorber. So all the water will get stuck there. It's like extremely hydrophilic, likes to attract all the water. While the CO2 vapor will just keep going. And the water will just get stuck here. Okay? And then we just need something to absorb the CO2, and we can use, for example, a base for that, sodium hydroxide, again supplied as a solid here. Okay, and then the CO2 will get stuck there. And then the remaining gases here, some remaining gases will go out, like O2, which was the reaction gas. We need to supply O2 here. So the O2 will exit here. And other gases, hopefully not, otherwise we have a problem to get like all the other ratios, but there might be some other compounds, like not only carbon and hydrogen, there might be some other elements involved as well in the compound. Okay? And then with this you can basically back calculate this. I'm not sure if we have like a example for this later. Maybe not, but we will see. Maybe there some example will come. Okay. Now, this will help you usually to get some kind of idea about the ratio of x and y. Maybe not directly x and y, but at least the ratio of x and y. This is what we usually call the empirical formula. So you get the idea about the ratio of x and y. So we can write this, for example, one example would be CH5N, and then with a small n here. And we don't know the n, we know the ratio of the elements. That's what we can get from this elemental analysis. But we don't know the exact number per molecule. Yeah, that's difficult to know. We can get the relative ratio, but not the exact number. This is what we call the empirical formula. So molecular formula, we know exactly per molecule how many atoms carbon, how many atoms we have. So for example, C2H10N2, right? This would be the corresponding molecular formula. Okay. Let me make some sense next. Okay, so we said molecular formula. Example would be like we have C10 and what's it? C10, C2H3. C2H10N2. This was our molecular formula. And the empirical formula was CH5N. So it has the smallest number of carbon, right? Carbon is 1. We don't want to go smaller than 1. We could make an empirical formula like C0.5, but we don't do that. We'll choose the smallest number, which is C1. And N is our empirical formula. My writing is so bad. Okay, and now in principle, we can determine that N by just dividing the molar mass divided by the empirical formula mass. Right? So take like the so take the mass according to the molecular formula. Divide by the mass of the minimum unit in the empirical formula. So that means we calculate the mass of the molar mass of C2H10N2. We divide by the molar mass of CH5N. And what we get in this case is 2. So this will be our N, right? This is a different N, this is not the mole number, right? This just tells us that we have 2 empirical units included in the molecular formula. It just tells us like about the how many units we include, right? Okay. So for example, C2H6, what would be the N here? 2, right? It is 2 times CH. Okay, this is I think clear. Okay, so now we do one example here. So we have a white powder which is analyzed and we find space. White powder is analyzed and we found it to contain 43.64% of phosphorus. And then we have 56.36%. That's the mass fraction of oxygen. The compound molar mass is known. It's 283.8. And the task is to get the compound's empirical and molecular formulas. Okay, so how do we do this? Okay, we know the percentage by mass and we know the molar mass. What do we need to get the empirical formula? Well, essentially we need to know the mass of each element in 100 gram of compound. So we could say, let's fix our total mass of the compound. We want to know how much of each of the elements is in there, right? So let's say for simplicity, we fix ourselves to 100 grams of the sample. Then the mass of phosphorus would be just 43.64 grams. And the mass of oxygen would be 56.36. Right? So that is easy. We can convert this to mole. Right? We can convert this number to mole. It's just m over the molar mass. And this is 1.4. Is 1.409 mole. And for oxygen, this would be 3.523 mole. So this would be the mole number in 100 grams of the substance, right? And then we can easily get the empirical formula for the compound by just dividing this mole number with a smaller one. So we can just take like 3.5 to 3 mole divided by 1.409 mole. This would be NO divided by NP. And this gives exactly 2.5. So we have 2.5 as many oxygen atoms as phosphorus, right? So our empirical formula should be PO 2.5. But we don't really like that one, so we multiply by 2, so it's P2O5. Right, so this would be our empirical formula. Oh, time is over. Sorry. I was too much involved with this small thing. See you on Thursday.